This tutorial will focus on acid-base neutralisation reactions. To understand the concept of an acid-base neutralisation reaction, you need to understand, of course, what an acid is. You need to understand what we call a base, and you need to understand what we mean by neutralisation. So let's first have a look at what we mean by an acid, because unless you understand what an acid and a base is, trying to understand neutralisation is very difficult. So when you take some chemicals that contain hydrogen and mix them with water, the solution becomes what's called acidic, and if it's strong enough, can become quite dangerous, in fact very dangerous. So if you took something like hydrogen chloride or hydrochloric acid, and you've dealt with this in the laboratory a number of times in recent weeks, so hydrochloric acid is HCl, is essentially hydrogen chloride mixed with water. So hydrogen chloride and water. The thing is that when hydrogen chloride is mixed with water, that the hydrogen and the chlorine separate and they form what are called ions, which are charged atoms. They have a little electric charge on them. And you end up with lots of hydrogen ions and chlorine ions in the mixture. And it's the presence of the hydrogen ions that give the solution, that's the entire mixture, its properties as an acid. And the more hydrogen ions that are present, the stronger is the acid. So there's a scale of strength in acids, from very weak acids, which have very few hydrogen ions, up to very strong acids, which have a lot of hydrogen ions. And very strong acids are corrosive. That means they will burn through other substances. They'll burn through your skin, they'll burn through paper, they can burn through metal. So very strong acids are corrosive. So strong acids, which have lots of hydrogen ions, are corrosive. Weak acids are not corrosive. And a weak acid, an example of a weak acid might be something like vinegar that you have in the kitchen, and you can eat it. Citric acid out of various things like lemons. So there are weak acids which don't do any damage and can be eaten. You've got strong acids which are very, very dangerous, and you've got a number of strengths in between. And we'll look at how we measure the strength of acids and bases on something called the pH scale shortly. So the strength of an acid is decided by the number of hydrogen ions that are dissolved in the water in solution. For a base is usually a measure of how many hydroxide ions are dissolved in water. Let's have a quick look at that. So a base is a chemical that when dissolved in water releases a lot of hydroxide ions. And hydroxide ions have this combination. So a hydroxide ion has an oxygen, a hydrogen, and has a negative electric charge on it, a hydroxide ion. So you can, again, like acids, you can have weak bases and strong bases, and the more hydroxide ions that are present, the stronger is the base. And like acids, very, very strong bases can also be caustic, very similar to corrosive. They can burn through substances, etc. A lot of our cleaning agents are made out of bases because they have this power to remove dirt and grime and so on. A common base that you've been using this year, even though in a very weak form like the acids, but the base you've been using is sodium hydroxide. Alright, so there's the sodium atom in A, and there's the hydroxide part of the formula with the OH present, sodium hydroxide. And when, of course, that's mixed with water, like acids, you end up with sodium. They separate, the sodium and the hydroxide, floating around in the water. and it's these hydroxide ions that give the base its various properties as a base. When it's dissolved in water, sometimes bases, when dissolved in water, are described as alkali solutions or alkaline solutions. So acids, strong acids can be dangerous, strong bases can be dangerous. And often in the world we don't want to be working with acids and bases because they often are dangerous, so we want to cancel them out, we want to get rid of them. And one of the best ways to do that is that acids and bases can actually counteract each other. So when you put an acid with a base, in just the right quantities, you can turn it into something quite harmless, like a salt and water. So the general equation, so acids and bases can cancel each other out, just in the right quantities. And this is what we refer to as neutralisation. And perhaps just before we get to looking at the neutralisation reaction, let's have a look at how acids and bases are measured. Acids and bases are measured on a scale called the pH scale. Let's have a look at how this works. In its simplest form, the pH scale is a measure of how many hydrogen ions or hydroxide ions are in a mixture, in a solution. And it's a scale measured from 0 or 1 to 14. So that in its simplest form, the acids are always measured between 0 and 7, and the bases from 7 to 14, or 8 to 14. Let's have a look at one in a little bit more detail. So here's another picture of the pH scale. Again, 0 to 14. And again, showing on the diagram that as you move to the left, so 7 is described as neutral. That is, it's neither acidic or basic or alkaline. And as you progress from 7 down towards 1, then the acid gets stronger. So this is increasing strength. So this is strong acids, and this is weak acids. This is weak bases. This is strong bases. And this is neither acidic, neither acid or base. So the pH scale is a measure of acidity or alkalinity, or that's the strength of bases. pH can be measured by chemicals called indicators. And acid-base indicators are simply chemicals which change colour depending on the strength of the acid or base that they are in. And this is very helpful to chemists because indicators can tell you the strength of the acid or base that you're dealing with, and can also tell you, of course, when you've reached a point of neutralisation. And just before we finish up this tutorial to look at acid-base neutralisation reactions, have a look at these two scales here. You can see the various colours that probably are linked to a particular indicator, and also a number of things out there in the world that all can be measured in terms of having a pH level, that is a level of acidity or alkalinity. Here's something like stomach acid, which is a very strong acid, pH 1.5 to 2, which means it's quite a strong acid that's in your stomach. Look at something like vinegar, a slightly weaker acid at 2.9. Orange juice has a pH of 3.5. Healthy skin has a pH of about 5. Pure water is neutral, it's neither acid or base, it has a pH of 7. Look at something like baking soda, it has a pH of 8.4, so it's slightly basic. Something like bleach is a very strong base, has a pH of 12.5. And there's a few other examples up here. Some of the common acid-base indicators are things like universal indicator, which you've already worked with. But you can find indicators in lots of natural products too, like the various pigments or colours in plants can be used as acid-base indicators. So universal indicator is a common commercial indicator. There are indicators with very strange names like phenolphthalein. There are indicators that are on papers called litmus paper, which can change colour in the presence of an acid or base, and so on. So let's finish up this tutorial looking at acid-base neutralisation reactions. So, like all the other reaction types we've looked at, there's a general equation, or a general equation to describe any acid-base neutralisation reaction, and it's this. So an acid plus a base will react together to make a salt plus water. And a common example, hydrochloric acid plus sodium hydroxide will make the salt sodium chloride. So there's that recombining sodium and chlorine to make sodium chloride, plus there's the hydrogen and the OH to make H2O, which is water. Interestingly, this is table salt, NaCl, and is utterly harmless because we put it in our food. But if we drank hydrochloric acid or sodium hydroxide, we would get very sick. So these are two quite dangerous substances, making two substances that are completely harmless, sodium chloride and water. So this is, any neutralisation reaction fits this general description. And as I have said to you already in this tutorial, if you add just the right amount of acid to just the right amount of base, you can end up with a neutral solution, that is a salt and water that is pH 7. And that's what you were doing during the titration. That was the use of the equipment of the burette and dribbling the hydrochloric acid into the sodium hydroxide to find the point at which it created a neutral solution. So to try and neutralise an acid or a base by adding the other is a process called titration. And this is what you did in the laboratory. So you had a burette, which was a long, thin cylindrical tube, which had measurements on the side, measured in millilitres, mils. You remember there was 0 up here down to a higher number down here. Then you had a conical flask or a beaker down here, and you had a little tap on the end of the burette that you could turn on and off, and it was held in place by a stand and a clamp. Then you filled up, in our case, you filled up the burette with hydrochloric acid, and in the flask you had some sodium hydroxide. And you remember, this is the base, this is the acid. And then you put an indicator into the sodium hydroxide, which turned it a pinky purple colour. And then you slowly added the acid, little bit by little bit, swirled the beaker around to make sure it was well mixed and that it was reacting, and you were waiting for the point where the pink-purple colour would turn clear. And at that point you would know that the amount of acid that you had added to the base will have neutralised it and created a neutral pH of about 7. So a titration is designed to work out just how much acid you need to add to a certain amount of base to reach the point of neutralisation, which on the pH scale means reaching a pH of 7. So it is neutral, that is, it's neither acid or base.